Hello students, welcome to the series of lectures on digital speech processing. So in this video you will be able to learn the classroom discussion topic on properties of the complex substrum and computational considerations. Okay, let's get started. So this is the lecture learning outcome. On completion of the lecture you will be able to list the properties of the complex substrum. So in the previous video we clearly introduced what is a substral domain and what is the difference between the terminology when it comes to the spectrum domain and then substral domain. Okay, so the same thing how we are going to be looking the properties of the complex substrum. That means before you understand the properties, first you need to understand what is a complex substrum and what is the real substrum. So like that you need to distinguish. Alright, so this is a terminology that we have already seen. So spectrum, which is a Fourier transform of the signal autocorrelation, but when it comes to the substrum, which is the inverse Fourier transform of the logarithmic of the spectrum. Okay, so this we can write like this. Just recall in the previous video we have clearly mentioned this mathematical expression. So C of x of t, where x of t in the time domain is equals to inverse Fourier transform of logarithmic of Fourier transform of x of t. So this is nothing but your substrum. Okay, and when it comes to the analysis, nothing but determining the spectrum of a signal. Okay, so this is in the normal conventional domain, this we already know. So to determine the spectrum of a signal we are calling that as an analysis, but when it comes to the substral domain we can call that as the analysis. Okay, so determining the substrum of a signal, that is only the difference. Determining the substrum of a signal. And similarly filtering, there is a linear operation on the time signal, but when it comes to the substral domain we can call that as a liftering, which is a linear operation on substrum. And when it comes to the frequency, that is the independent variable of a spectrum, and we can call that as a Q frequency, independent variable of a substrum. And in the previous video we clearly mentioned the visualizing, how we need to visualize the substrum and what is the x-axis and what is the y-axis. On x-axis we can call that as a Q frequency in the milliseconds. On y-axis we can call that as the absolute magnitude. And when it comes to the harmonic, that is the integer multiple of the fundamental frequency, but when it comes to the harmonic, okay, in the substral domain we can call that as a harmonic. So it is an integer multiple of the fundamental Q frequency. Okay, there is a mistake here. This is a Q frequency. Okay, so this we are going to be looking for understanding the substrum and what is a real substrum, what is a complex substrum, and what are the properties. Now, so the term substrum was introduced by Bogart and we clearly mentioned in the previous, but when it comes to the complex substrum, which implies that complex logarithmic is involved. Okay, so if that signal is involved the complex logarithm, then we can call that signal as a complex substrum. Now, so to distinguish what is a complex substrum, what is the real substrum, because we are already getting knowledge on what is a substrum. Now we are focusing what is the real substrum and then complex. So which define the inverse Fourier transform of x cap of e power j omega, that can be given in the mathematical expression, like this we already know, normal z domain. So inverse z domain. So x cap of n equal to 1 upon 2 pi. Integration starts from minus pi to pi, x cap of e power j omega into e power j omega d omega. So where this x cap of n is called as a complex substrum. On what basis I am telling this? So on the basis of, because complex logarithmic is involved here. Okay, so here there is a involvement of the complex logarithm. So therefore we are calling that as a complex substrum. And we can also define this as a real substrum, but using only just the real part of the logarithm. So when you take only the real part of that, then we are calling as a real substrum. Okay, now how we can write in the mathematical expression is C of n equal to 1 upon 2 pi integration minus pi to pi, the real part of x cap of e power j omega. Okay, but when you see here, the complete signal we have taken. In the complete signal, we can consider, both real and then imaginary terms which are there. Okay, but when it comes to the real part of x kappa p power j omega, only the real terms we are collecting. Okay, now, so 1 upon 2 pi integration minus pi to pi, we can also call this as a logarithmic of mod of x of e power j omega. Okay, so this can show that c of n is the even part of x cap of n. Okay, so the c of n is a normal cepstrum, the real cepstrum, which is an even part of the x cap of n. Okay, that also we can prove. Now, so when you see both the mathematical expressions at one place, so this is the way we are going to be looking. The real cepstrum c of n is a even part of x cap of n. So x of n, x cap of n equal to 1 upon 2 pi integration minus pi to pi logarithmic of x of e power j omega into e power j omega n. This is nothing but the complex cepstrum. When it comes to the cepstrum or the real cepstrum, we are taking the magnitude. That is only the difference between the two equations. Okay. Now when it comes to the properties of the cepstrum, the first property we need to remember, so the complex cepstrum is non-zero and of infinite extent for both positive and the negative value of n, even though x of n may be causal or even of the finite unit. This is the first important property we need to look into that. And the second important property is that the complex cepstrum is a decaying sequence and that is bounded by like this. Okay. And third one, the zero Q-frequency value of complex cepstrum. So see here, we are not calling this as a frequency. This is a Q-frequency because in the cepstral domain we are calling that as a Q-frequency. In the spectrum domain we are calling that as a frequency. Okay. When it comes to the zero Q-frequency value of the complex cepstrum, which depends on the gain constant and the zeros outside the unit circle. Okay. So this is the way how we are going to be calculating the gain magnitude. Now, next property number 4. If x of z has no zeros outside the unit circle, then x cap of n equal to 0. This we are calling as a minimum phase signal. And similarly, when you look into the property number 5, if x of z has no poles or zeros inside the unit circle, then x cap of n equal to 0 when n greater than 0. That signals we are calling maximum phase signals. Now, so when it comes to the jet transform cepstral analysis, okay, it is not analysis, it is analysis, because in the cepstral domain we can call analysis as analysis. So in the cepstrum domain we are calling that as cepstral, not the spectral. Okay. Now we are going to be representing the transfer function in a all pole zero method. Okay, so this is the all pole zero method we are going to be considering. So where x of z equal to the roots of the numerators are nothing but zeros, the roots of the denominator are nothing but the poles. So like that we are going to be calculating all the coefficients which are associated with the equation that you are seeing on the slide. So with all coefficients, that is ak, bk, ck, all the parameters of the coefficient which are less than 1, and all ck poles and ak zeros are inside the unit circle. Okay. So this is the way how we need to understand the all pole zero method. Now we need to express x of z as a product of the minimum phase and the maximum phase signals. The sequence actually we need to follow. Now when it comes to the properties of the complex cepstrum, so given a complex logarithmic which satisfies the phase continuity condition, and we have x cap of n equal to something like this, and if x of n is real, then log of mod of x of e power j omega, which is an even function of omega, and argument of x of e power j omega. So the most important property that we need to remember here is that the C of n is the summation of x cap of n plus x cap of minus n divided by 2. This is very important property, and we can also see the proof of this statement, that is C of n equal to x cap of n plus x cap of minus n by 2. It is very simple, because once we know how we need to represent the mathematical expression of the cepstrum and then complex cepstrum, okay, it is very easy. The only thing what we are doing here is that we are taking the assumptions, some of the assumptions we are going to be considering, and the way how we are going to be looking for satisfying the condition that you are seeing on the rectangular box. So this is the relationship of the complex cepstrum to the real cepstrum. We clearly mentioned in the previous slide also the way how we are going to be seeing this. The real cepstrum is a C of n, x cap of n is a complex cepstrum. That is the relation between these two. Now, so this is the proof I clearly mentioned. Once you know the mathematical expression of the x cap of n, the complex logarithmic that has been involved, and when it comes to the e power j omega n, we have expanded like this. Okay, e power j theta cos theta plus j sin theta, like that we have expanded. And for x of n real, this argument of x of e power j omega is an odd function, therefore which integration equal to 0. And similarly, we are going to be taking in place of n, if you take minus n, this is the way how we are going to be looking the equation. Okay, and if you observe carefully, and you will be getting x cap of n plus x cap of minus n by 2 equal to c of n. So this is the way how we are going to be proof of the statement that you are seeing on the top left side of the slide in the rectangle box. So this is the computational considerations. Okay, and from this also we can clearly see that if you want to see the c cap of n, that is the Sepstrum domain, what we are doing here, the logarithmic magnitude we are going to be considering. But when it is the complex, so these two are the complex Sepstrum, this is a real Sepstrum. Okay, so this is the way how we are going to be distinguishing, the way how we have arranged the block schematic for the considerations. And this is the basic speech processing steps for the frequency parameter that we already know. When you take the speech signal as s of t equal to x of n, first we need to pre-emphasize that signal, and then we are applying the framing method. Okay, we are dividing that entire duration of the sequence of the signals into the different frames, frame 1, frame 2, frame 3, like that, and then we are going to be applying any kind of the window that you wish to apply. If you take the Hamming window, what is the characteristic response of that, and then Hamming rectangular. Okay, so normally we can apply the Hamming or the rectangular window, and then we are applying the discrete Fourier transform. So when you apply the discrete Fourier transform, this is the way how we are going to be analyzing the frequency spectrums. Thank you, students. Thank you for watching this video.